Hello, my name is Zachary Booker, and this is my third Physics 2212 lab for this semester. And in this lab, we will be working with magnetic fields trying to determine the magnitude of the magnetic field of a bar magnet using our formulas. Introduction. The purpose of this lab is to analyze the connection between magnetic field and distance, both on and off axis, to further our understanding of the VPython law, which relates magnetic field with displacement and the magnetic dipole moment. The result of my project showed that my magnetic dipole moment was 2.67 joules per Tesla, and my magnetic field was proportional to the distance by a negative 3.129 power. I'm sorry for the typo right here. This should not be there. Procedure. Determine the direction of the magnetic north. Line the phone flat on the table and rotate it until the x component equals 0. Set up the meter stick orthogonal to the north. Locate the magnetic meter of the phone. Slide phone perpendicular to the stick in the x and y direction. Move the phone at various distances along the meter stick on axis at 45 degrees. So computation. Observe that the magnitude of a magnetic field is equal to k times r to the raised by n. We will be assuming that n and k are constants, and we expect that should be very close to -3, which is before was what r is raised to in our magnetic field formula. And here's some measurements for my data. So using some logarithmic manipulation, I'm so sorry for my stutter. Using some logarithmic manipulation on the previous formula right here, we can turn that exponential expression into a linear line, given this data set and these points. You should notice that this is our finding from earlier, because the slope of this line should simply just be, well, and k should just be equal to the y-intercept. So by using the natural log in the formula given by the slide before the last slide, we can linearize our data set as shown in this Excel file. The slope of the line is defined for the proportion between the distance and the magnetic field, and L and K is just the y-intercept. Therefore, we can use this to solve for the magnetic dipole moment, and this would be found by either using simple algebra or also using VPython. I'm also sorry for not putting magnetic field here, which doesn't have it. Now, instead of placing our phone on the axis, we have to place our phone on the 45-degree to the bar magnet, where dperp, the average for dperp equals 0.19 meters, and the average for the magnetic field being 1.6776 to 10 to the negative 4 power Tesla. And these are our results from our computation model in VPython. As you can see, our components are very different, because in our Excel file we were able to find an x, y, and z component to our model, whereas in our Python model we noticed that there was actually no z component, which is a very interesting finding, considering that Python will obviously be a very ideal scenario. And in this slide, I basically previewed this slide with my last statement. We could see that since our computation model was an ideal setting, this could imply that there's either unknown electric fields acting on our data, which is very possible since we have a lot of electronics around in modern day. There's just a ton of electronics that could produce their own magnetic field, or it could just be human error, which is a very real possibility in an undergrad level lab. Closing remarks. What if we didn't account for the magnetic north? Well, our findings would be significantly less accurate due to a skew in the magnetic north direction. And also, what if we stuck two magnets together? How would this change our data set? I believe that the direction would be the same, but the magnitude would increase because of the larger magnet. And this has been my lab. Sorry for any inaccuracies, and have a good day.